Hello mathematicians, this is just an unusual little section about intercepts and sines which just gives you maybe a little bit of background information about sketching unknown graphs. So when we're sketching unknown graphs, we usually find the y-intercepts by putting x equals 0. If we can, the x-intercepts by putting y equal to 0. And then whatever other clues we can find. So some of the things which are relatively easy to find are restrictions on the domain if they exist, which might give rise to discontinuities. And then we could simply take a point between interesting bits, like intersections on the x-axis and discontinuities, to get an idea of the general shape of the graph. So we'll have a look at these with these examples below. And it's just like you do these as a first guide towards how to set up the graph. Now for this first example, we recognise that as a parabola, and it's going to cut at -1 and -3, and we know that it will be concave up, so we wouldn't have any problems with it. But let's suppose we had no idea. We look at this and we say, well, let's find the where we cut the y-axis. So we put x equal to 0, so that will be 1 times 3, so that will cut at 3. Find where it cuts the x-axis by putting y equal to 0, so that will be -1 and -3. Now if we had no idea after that, which is hard to imagine, but if we had no idea after that, what we could do is just take these points here and pick any point in between them and have a look at the sign of the answer. Not so much the value, but just the sign. So if I took -2, for example, which we know is the x-coordinate of the vertex, but if we took -2 and I put -2 plus 1 and -2 plus 3, without even working it out, this bracket is negative, this bracket is positive, a positive times a negative is a negative, and we therefore know that we're below the axis here, and we must be above it on the other sides. So as I said, a bit of overkill there, but it demonstrates the technique with an example that we know the result of. For our next graph, well, our next graph is a cubic, because we've got x cubed as the highest power. We know it's going to cut through the x-axis where x equals 1. So it will cut through that one, and it will touch the axis at x equals -2. So we know something about the curve. Now we can find where we cut the y-axis by putting x equal to 0. So that will be -1 times 4. So that's -4. And really, in a sense, we're done, because if we have to pass through here, we're just going to touch there and we're going to cut through there, then we know that the only possibility is if the curve goes something like that. Okay, and for our next example, we've got 1, 2, 3, 4 x's being multiplied together. So this is a quartic, so it could have up to 3 bumps on it. Our cubic had 2 bumps, our parabola had 1 bump, so 1 less than the maximum power. Now, where does this parabola cut the x-axis? Well, it will cut at x equals 2, at x equals 0, at x equals -2, and at x equals -4. And if we think about this curve, then it could go down this way, like that, or vice versa. Now, it's got to fluctuate around. We just need basically to test a sign somewhere. And we might as well find where we cut the y-axis. So we cut the y-axis when x equals 0. So that will be -2. Oh, that's no good, because that just gives us 0. Obviously, we've got that already. Okay, so one other point. So let's put x equal to 1. So if I put 1 into this bracket, that becomes negative. This one, the x is just positive, this one is positive, and this one is positive. So I've got a negative times 3 positives. I'm going to get a negative. So I know that this graph I haven't got any idea of the scale, but I know it runs that way in general. Now, it doesn't mean that all of those bumps are at even heights, but I just know that that's the general shape of it. Now, while the examples up above were just to give us a vague idea about the shape of a curve, this example here is actually a useful application of this concept. So when we've got an inequality, this might be a technique which we can pursue. We've already had a look at how we could do this in section up above, where we could multiply right through both sides by the square of the denominator. So I won't do the whole process, but we could have this multiplied by x plus 3 squared greater than or equal to x times x plus 3 squared. And then we could try and solve it. But what we'll end up with on the right-hand side is a cubic. And on the whole, we haven't got any method of dealing with a cubic just yet. That will come in polynomials. So there's an alternative using this concept up above because of the fact that it's an inequality. And that alternative involves, first of all, gathering everything to the same side. So 4 over x plus 3 minus x greater than or equal to 0. So what we're really looking for is when this curve, whatever it looks like, is above the x-axis. So when it's greater than or equal to 0. So if we just work on this side now, get a common denominator. So our common denominator could be x plus 3, or will be x plus 3. So that will go 4, and 1 will go into x plus 3 times. So it's minus x times x plus 3, greater than or equal to 0. Work on the top. So the top is then minus x squared minus 3x plus 4 all over x plus 3 greater than or equal to 0. Now if I then made that minus outside of x squared plus 3x minus 4 all over x plus 3 greater than or equal to 0. Now I could do something with the negative, I'll worry about that in a moment. Let's try to see if we can factorise this. So two numbers that multiply to give us minus 4 and add to plus 3. So we could have plus 4 and minus 1. Now, just to make it look tidier, I'm going to divide this negative through. So I get to this. So I've got to change the inequality. And what do I then know? I know that this thing, if I graphed it, is going to cut the x-axis at 1 and minus 4. So 1 minus 4. We're not allowed to have x equal to minus 3. So there'll be a discontinuity just there. And I can think about what my curve looks like on either side of that. So when x equals, when this expression actually equals, let me start that again in English. So when x equals 0, I'll have plus 4 times minus 1, so it's a negative over a positive, so that's a negative. So between the discontinuity or the point where it cuts the y-axis in a nutshell is negative something or other. So we're down here, negative. To the right of the value of 1, so if I put 2 into this, for example, 2 plus 4 is a positive, that's a positive, that's a positive, so I'm up above the axis over here, and I'm down below it here, and I know I'm not allowed to equal that. And on this side I've got between minus 4 and my discontinuity, so if I put say minus 3.5, then this bracket will be positive, this will be negative, so the top line is negative, the bottom will be negative. Negative divided by a negative means a positive, so I'll be up here somewhere. And I'm cutting through the axis here, so I'm going to go down like that, but I can just check. If I put -5 into it, this will be a negative, this will be a negative, so the top is a positive. The bottom with a -5 in will be a negative, so positive divided by negative gives me negative. Now, all of this doesn't mean that this is anything like the shape of the curve. Well, it doesn't mean it's anything like an accurate drawing of the shape of the curve, but I do know that the curve is positive in this gap, negative in this gap, doesn't exist here. It's negative in this gap, and it's positive past there. And what I was interested in was where this curve, whatever it really looks like, is less than or equal to 0. So where is that the case? Well, it's the case for any x values going that way and including this x value, and it's the case for any x values between here and here. I can't include that one because it's a discontinuity, but I can include that one. So if I translate that to an inequality, that means that this will be true for where x is less than or equal to -4, and where -3 is less than x, which is less than or equal to 1. Now, just here's a nice little caution for you. So this process is fine as a process, and we got the right result for where this statement up here is true. But this thing that we did here, like I said, it's not a picture of the graph, and it's not even this graph here or that graph there, but it's a tool for us to be able to get the right answer for the inequality. I just thought I would show you the actual graph of this, 4x plus 3 minus x. And remember, we wanted where that original expression was greater than or equal to 0. So if I can bump that graph up there, this is what that graph looks like, 4 on x plus 3 minus x, which is nothing like this graph because this was just a tool. This actual graph is this one here, and where this actual graph is greater than 0 is up here, which is where x is less than -4, and in this bit here, which is where x is greater than -3 but less than or equal to 1. And finally, a little teaser for you. Right towards the end of this chapter, we look at different ways of using graphs, but this is a good question to look at. If I look at the graph of 4 over x plus 3, then that's this hyperbola here in green, this continuity at x equals -3. And I look at the graph of y equals x, that's our black line here. So this is saying, where are the y values on the hyperbola greater than or equal to the y values on the line y equals x? And interestingly enough, the hyperbola is higher up than the straight line for this part of the curve, which is x less than or equal to -4, and for this part of the curve, which is for x greater than -3, less than or equal to 1. So just tuck that away in the back of your mind. Okay, so if you now have a look at these questions out of 3B.